think we may continue. So now, José Miguel has explained how to deal with images in 2D. Now we'll move to 3D, that is our final goal. So these are the topics that we'll cover during this hour. So how to work a little bit with the initial volume. We'll see that it is a big problem. Then how the angular assignment is done. That means you have your experimental images, you have to decide each experimental image from where it is seen with respect to a volume. Then how do you do the 3D reconstruction? How do you classify your images into, if you have an heterogeneous sample? And then how to calculate the resolution. Then an issue of amplitude correction. You remember yesterday from the CTF, normally the phase is corrected at the level of the micrograph, but the amplitude is corrected at the level of the volume. And then how to avoid overfitting. Okay, so this is our goal. So our goal is to take our projections from the micrographs, each one of these boxes here, and to combine them into a 3D reconstruction, like this one here. So there are several steps. So the first step, the whole thing going from here to there, with respect to the 3D processing, all of it normally fits into this structure of projection matching. So projection matching, you can do it in many different flavors, but the general idea is the same. So you start with some experimental images, like those ones. Then you take an initial volume, something that is related to your structure, but it is not your structure. Then you try to project your volume into all different projection directions that you can imagine, and you have a gallery of reprojections from your initial volume. Then you do a matching, and you say this experimental image is most similar to this one, to this reprojection. This experimental image is most similar to this one. Since you know the angles from where these two reprojections were taken, so you assign those angles to the experimental image. And now you make a 3D reconstruction. Now you combine back all these experimental images with their own angular angles back into the 3D, and this is called the 3D reconstruction. And now you have another initial volume, and you reiterate, you go back to the reprojection step, and then matching, reconstruct, and you iterate this process many times. So this projection matching is a greedy algorithm. So if you think of the goal function that you are optimizing, what happens is that you start with an initial condition, an initial volume, and you try to go to the global minimum, hopefully. Normally you go to a local minimum as fast as you can. That is why you go to a local minimum, because you try to go very fast. So this is another representation. This would be your goal function, and within your iterations, what you do, you start with your initial volume, then you modify your initial volume to a different volume, and then you modify, further modify, and at the end, hopefully, you will converge to the global minimum. So the real life is that the goal function looks more like this. So there are a lot of local minima. You want to reach your global minimum, and there are different strategies trying to converge better to this global minimum. So you have a function that you are minimizing. Normally it is the difference between your experimental projections and the reprojections of your volume. So this is your volume, you reproject with some angular parameters and some shifts, and this reprojection should be as similar as possible to your experimental projections. So the difference, in principle, should be just the noise. So you are trying to minimize the variance of this noise. So you have to minimize this function with respect to two things. One is the volume. So the volume, for instance, if you have a volume of 200 pixels in size, your volume has 200Q parameters. So you have to find 200Q values. That is, those are the variables defining this goal function. The other parameters that you have to optimize for are these theta. Theta are the angles and the shifts of each one of your experimental images. So let's say you have 100,000 projections, so you would have 5 parameters per projection, so 3 angles and 2 shifts, and you would have 500,000 variables to optimize. So overall, you have about 8 million parameters to optimize. So we are defining a function. This landscape is defined on two variables, x and y, and then for each x and y you have a landscape A. So instead of 2 variables, you would have 8 million variables. So you have to optimize. This is a daunting optimization problem. So it is very easy to fall into local minima, and there are ways to try to avoid it. The best thing is that your initial volume starts in a place that is close to the global minimum. So the closer you start, the more chances you have to go to the true minimum. And there is this concept in electron microscopy that is model bias. This model bias, there is a very nice example in this paper. So you take 1,000 images of just noise, pure noise, there is no structure in it. You align it to a reference, and now after alignment you compute the class average of all those aligned images, and this is what you get. So you recover the structure. So you put a reference, and what you recover is the reference. So this is very important. This is in fact the model bias in electron microscopy. Is in fact the local minimum in the optimization field. So you start with a point, and you convert to a point that is the closest to the original point that you started from. So it is very important to start with a relatively correct structure, because otherwise you will convert to something that is nonsense. So how to choose the initial volume? So the first option, and this is one of the most widely used, you take a structure that is related to your problem. So for instance, let's say you are reconstructed ribosome. So you take a ribosome that is more or less similar to yours, and if you have an atomic structure of that ribosome, or you have a filter version of that ribosome, doesn't matter. Normally you filter it, low pass filter, very strongly, so that you keep the general features but not the detailed features. Okay, so you filter it normally at 80 angstroms, 100 angstroms, so you simply keep very general shape of your structure, and then this is your initial volume. So this is one possibility, and it is very much used in fact. Another possibility is that you construct a phantom of your structure. So you say, oh, I know my structure a little bit looks like this, it is an hexamer with some arms coming out from here, so I put some ellipsoids, some spheres, so that it resembles more or less what I want. And we have, for instance, a program to do these things, and once then you convert this geometrical description into a volume, and you use this volume as a starting point. This is adding a lot of a priori information, so you need to really know how your structure looks like, because we have seen this model bias. So if you put the wrong structure, what you will recover is your input structure anyway. Then hopefully this should work. That is, you put just noise or just a blob, and you hope that the algorithm is strong enough, robust enough to escape from this initial structure and to go to the correct structure. Sometimes it works, sometimes it doesn't work. For instance, in Iman, this is one of the strategies to start the reconstruction. The other possibility is to go to the microscope and to do a random conical tilt. So random conical tilt, you take 2 pictures of your sample, of the same sample, the same grid, and one of the pictures is untilted, so it is perpendicular to the electron beam, and the other one is tilted, this one, so that here you have the 3D or you have the structural information to reconstruct in 3D. Here you don't have enough information. So the trick is that you can relate the positions and the angles between each one of the particles. For instance, you may say this particle here is this one here is this one there, and by aligning these particles among themselves, from that alignment and the tilt angle that you know, you can recover the angles that you need for doing the 3D reconstruction. So this is another possibility. Here you have a problem because you cannot tilt 90 degrees because otherwise the electrons wouldn't pass through your sample. But so this limitation on the maximum tilt translates into a region in Fourier space that you don't have any information, and this translates into elongations along that direction. But apart from these elongations, it is a good starting point for doing a 3D reconstruction. This random conical tilt is based on this central slice theorem. The central slice theorem tells you that if you have an object that in 3D that you want to reconstruct, and you take a projection out of it, this would be the experimental projection that you get in the microscope, and you compute the 2D Fourier transform of this image, then you are back, or you are in Fourier space with a 2D function. So this 2D function is in fact a plane of the 3D Fourier transform of this object. So you compute a 3D Fourier transform of this, you are here in the 3D Fourier space, you compute the 2D Fourier transform of this image, you are in the 2D Fourier space, and this plane fits somewhere in the 3D Fourier transform of the object. And this somewhere is always through the origin, so it is a plane passing through the origin of the Fourier space, and all you need to know are which is the right orientation of that plane, those are the Euler angles, and which is the shift of this image with respect to this object, and this is encoded in the phases of the Fourier transform coefficient. So the random conical tilt is exploiting this, and by taking these two images, the untilted and the tilted, what you are doing is filling the 3D Fourier space in this way, so that you are filling each projection that you have in the tilted image, these projections here. If you take boxes around each one of the particles and compute the 2D Fourier transform, you would be, each one of those 2D Fourier transform would be a plane passing through the origin. The more planes you have, the better you are defining this area here. And this is, you can imagine there is a cone that you have not filled, because the planes they don't intersect in there. So this cone is the missing region. This is the missing cone that is provoking these elongations along this direction. So the other possibility is to use some computational means and then hope that the algorithms are good enough to find a good 3D starting point. So there are two main families. One is based on common lines that we'll see now, and the other one in stochastic optimization. So the common lines, what says is, okay, so if I take one projection, I do the 2D Fourier transform, I take another projection, I do the 2D Fourier transform. Since these two 2D Fourier transforms are planes in the 3D Fourier space, so let's say this is this plane, let's say this is this plane, they have to intersect into a line. So the coefficients along this line in Fourier space have to be the same in both planes. So I have to identify which one of these lines, of all the possible lines in the 2D Fourier transform, is the same in the other Fourier transform. So in this example, this line here would be the same as this line there. And by knowing which line goes with which, you can recover through a matrix, you can recover what are the Euler angles of your structure. So this is the idea of the common lines. So two projections are two planes in the 3D Fourier space, and they intersect into a line. So I have to find those lines. The other possibility is this stochastic optimization. So I have a function that I have to optimize, and then what I do is to assign random angles to each one. For instance, let's say you do it with classes, like those classes there. So you assign random angles to each one of the classes, and then you keep in some way trying to optimize this, but in a random way. So, for instance, simulated annealing is one of the most famous approaches. So you change one of the angles. So let's say I move this projection to there. If it fits better with the data, with the 3D reconstruction that I have already, then I keep it there. If not, I keep it there with some probability. So I'm going in the wrong direction. Instead of minimizing the function, I'm increasing the function, but I do it with a certain probability so that in the limit it can be proved that if you do it in a controlled way, this heuristic approach minimizes really the original function. Okay? So you keep changing randomly the angles, and at the end you hope that you find the global minimum. There are convergence theorems in the infinite long run. So if you run it forever, you are sure that you can reach the global minimum. Normally you never run it forever. So in practice you get trapped in local minima too. And so we have seen different possibilities to get the initial volume. Once you have the initial volume, you have to do the angular assignment. And the angular assignment means trying to find which is the reprojection from your initial volume that better fits your original data. So you decide that this experimental image goes with this image with these alignment parameters in plane rotation. You see it has been rotated to fit this one and this shift, and you know from this image, from this reprojection, which are the projection direction, so you assign those angles to this one. And if you have a symmetric particle, then the problem is simplified because you don't have to reproject from absolutely all projection directions, but you can, for instance, say this is Groviel, so it has D7 symmetry. So D7 means it is, if you rotate this by 360 divided by 7, you get the same volume, and if you turn the volume up down, you get again the same volume. So that means that projections, there are many projections that are actually the same. So you can simplify your search space, and this is not only a speed up, but also makes the problem more robust. You have fewer variables to optimize. And this is even more stronger if you have any icosahedral virus, then you have 60-fold symmetry instead of 14-fold symmetry. So the problem is simpler. And how do you compare your experimental image to your reference image? So you can do it in many spaces. For instance, you can do it in real space. This is the most standard approach. Then you can simply compute the correlation between the two images. But you can also compute it in Fourier space. For instance, every line is computing the distance between the experimental and the theoretical reprojection in Fourier space. We have some papers doing it in wavelet space. Michael Nadermacher does it in radon space. So you can do it in many spaces, and the different spaces help you to avoid local minima or to be more robust with respect to whatever. In fact, you see this is a long list of articles related to the initial volume and the 3D alignment. Many times they are intermixed, both problems are solved at the same time. So I have put the list of papers together. But I think we have a general idea of what is done in this respect, and then now we know the projection directions. We have to update our initial volume. So we have to produce a new volume that is more consistent with the experimental data. This is called the 3D reconstruction, and the 3D reconstruction, again, there are several families of algorithms. The first family would be direct Fourier methods. So since we know that each projection is a plane in the 3D Fourier space, we simply have to reinterpolate the 3D Fourier space into a regular grid and then do the inverse Fourier transform. So this is relatively fast. Normally it produces rather high resolution volumes, and there is a drawback that normally it needs enough particles. You can imagine that if you have large empty regions in Fourier space, it is difficult to interpolate in those regions. So if you have a good angular coverage and with dense, relatively dense filling of the Fourier space, then this method is rather good. Then you may be at the opposite side. You may have a rather incomplete angular coverage. For instance, this one is rather incomplete. We have a missing region. Or you have very few particles. Then you may resort to these iterative methods, and most relevant are R, SIR. They have a problem. They are rather slow compared to the other one, to the direct Fourier. And they have also the advantage that they can be very flexible with respect to the constraints you can put. You are solving not only the 3D reconstruction problem, but you can add a priori information. Like, I know that the mass of my particle is this one, and you can give this constraint to the algorithm. I know that my particle is symmetric. I know that the external surface of my particle is this one. So you can give many different constraints to the algorithm, but it is slow. And then we would have the weighted back projection. Weighted back projection could be said to be the traditional approach. It was the first approach to be applied. And the idea is that if you have different projections, I have plotted it here in 2D. So this would be our volume, this would be our projections. So in this example, the volume is 2D and the projections are 1D, but we can imagine we have plots for 3D and 2D. So the idea is that you take your 1D projection and you back project it. So I know that there is an object that, when projected into this direction, gives this function. So it is 0 everywhere except in a small region, that is 1. So I draw something that, when I project it into the same direction, gives this function. I do the same with this, so I back project into this line, I back project into this line, and then if I back project many projections, at the end, here, what I will have is my object. And this would be the traditional way. No, I would say this is no longer so much used. So normally the two used algorithms, so two families, are direct Fourier inversion or the iterative algorithms. This one is just when you want to compare with something else or whatever. But normally you don't use this. And again, there are many papers related to 3D reconstruction, in different flavors, different algorithms, etc. Then let's say you have an heterogeneous sample. So you are, for instance, in this example, they were reconstructing ribosomes, and they had two populations of ribosomes. One of these tRNAs here, and the other one with these factors attached. So in the experimental images, normally you don't see anything. So they have a lot of noise. You can not distinguish whether a projection belongs to this kind of structure or to this one of structure. So you rely on the computational algorithm to sort the particle into different classes, and at the end, what you hope is that somehow you are able to distinguish between the two classes. So you say all these projections belong to this class that are with the tRNAs, and all these projections belong to this other class that are the ones with the factors. And you hope the algorithm to do that for you. And 3D classification and 3D reconstruction, they are a little bit intermixed. It is a little bit like the chicken and egg problem. So you cannot reconstruct well if you have a mixture of populations. So if you have a set of images that belong to two structures and you do a 3D reconstruction, what you will have is a mixture of the two structures. But also, you cannot classify well if the images are not well aligned. So if my images are unaligned with respect to the volume, I cannot classify. I cannot distinguish which, if this particle has TRNA or this particle has factors attached. So for reconstructing, you have to classify, and for classifying, you need to align. So all the problem is intermixed. So there are a number of algorithms solving both problems at the same time. This is a little bit the same as the ML2D and CL2D. CL2D and ML2D are also solving the alignment and classification problem at the same time. And in fact, ML2D, the extension into 3D is this ML3D, and this here. So the idea is that all experimental 2D images belong to all 3D volumes, but with different probabilities, and you let the probabilities evolve along the iterations. In the limit, what you would have is the more classical multi-reference alignment. So one experimental image belongs to a single 3D volume. So you have to decide to which one of the 3D volumes that you're reconstructing it belongs to. And then this Bayesian prior, that is, for instance, Relion is using a Bayesian prior, is adding on top of maximum likelihood. So all images belong to all classes, but on top of that, I know a little bit how the 3D volume should look like, and should look like statistically. So what is the distribution of the Fourier coefficients in the Fourier space? With respect only to 3D classification, so here we are not solving the alignment problem, we have the bootstrap approach of Pavel Pensek. So let's say you have already aligned your images correctly. This is a very strong assumption because you never know if you have them aligned correctly. Then you choose any images randomly and you construct a 3D volume. And you repeat this process many times. So after many times, you can analyze what are the differences between the different random 3D reconstructions. And this is where you identify that there are big differences. Now you concentrate on those areas and try to classify your images with respect to those areas. Another possibility is to compute this map variance. The principle is similar, so you make many 3D reconstructions out of the same set of data, and then you try to analyze locally what is the variance of the volumes. So you know this is one of the steps in this bootstrap algorithm. So you realize this region is very much changing, and this other region is not changing so much. And again, there are a number of papers related to all this. And now you are happy with your 3D reconstruction. So the next question is, okay, so how much can I trust my reconstruction? So what is the maximum resolution that I can trust in this 3D volume? So the standard response is this Fourier shell correlation. So in fact, it is a measure of repeatability, not a measure of resolution. So what it does is you take your original data set of images. So let's say you have 100,000 particles. So you buy 50,000 particles in one set, 50,000 particles in the other set. You do two 3D reconstructions, and then you compare the two 3D reconstructions. So you go to Fourier space. This would be the 3D Fourier transform of your volume, 3D Fourier transform of your volume, and then you take regions that have the shape of a shell. Here it is a ring because I'm doing everything in 2D. And then you compare the Fourier coefficients along this ring in this volume and along this ring in this volume. And you decide how much they correlate to each other. So the more they correlate, the more you trust your 3D reconstruction. And in fact, this is a measure of repeatability. Let's say that your algorithm gives complete crack, but always the same crack. So the two volumes would be very much comparable. Okay? So this is in fact repeatability, not resolution. And there is a long debate of what should be the threshold for the Fourier reconstruction. There are a lot of families again. People saying 0.5, 0.143. There is a threshold with a correlation. What is the expected Fourier correlation of noise, and the half bit of Marin-Van Heel. So at the end, you have a curve of Fourier correlation. So this is at each frequency how the two volumes are correlating. At the low frequency, they correlate very well, and the correlation starts degrading. So you have to decide at which point I stop believing or trusting my volume. Okay, so let's say 0.5, like in this figure. So you would trust it up to this is frequency. The resolution would be 1/d, so about 25 angstroms. And what you hope with the 3D projection matching algorithm is that the Fourier correlation improves over iteration, so that you can trust more and more your volume as you progress in these projection matching iterations. Another family of algorithms are working with the spectral signal-to-noise ratio. So it tries to measure what is the power of the signal in Fourier space, what is the power of the noise in Fourier space, and I trust my data as long as I have more signal than noise. And so I compute the ratio between the two, and when the ratio is 1, then I stop there trusting my volume. I have more beyond 1, below 1, you have more noise than signal, so you don't trust your volume anymore. So you get a curve, and then there is a clear cutoff. There is no so much debate about what is the threshold for the spectral signal-to-noise ratio. So it is 1, or if you put it in decibels, it is 0 decibels. So here would be where you trust it. So one advantage of the signal-to-noise ratio is that you don't need to collapse all this information into a single curve. You have the full 3D information in Fourier space. So you have the full distribution of what is the spectral signal-to-noise ratio for all possible directions in your Fourier space, and you would get something like this. This is the Fourier representation of the spectral signal-to-noise ratio, and we have here two thresholds just for illustration. So let's say this is the mesh is the threshold for signal-to-noise ratio 1. So that would mean there are certain directions in Fourier space where you have a lot of information. You have the signal-to-noise ratio is rather high, while there are some other directions in which you don't have so much signal-to-noise ratio. And in fact, this example corresponds to a case in which there were a lot of top views and very few side views. So in the top view direction, you had a lot of signal-to-noise ratio. In the side view direction, all these directions, you don't have so much spectral signal-to-noise ratio. And now, recently, it has been published a paper trying to estimate locally what is the resolution and trying to attach a number to each location in the 3D map. So you would have a 3D reconstruction, and then for each point you would have what is the local resolution. So for this point here, it would be something around 10 angstroms, and for this point here, it would be something around 8 angstroms. So this is useful, and in the future I foresee that more algorithms in this direction will appear. And again, a lot of algorithms and a lot of papers related to how to measure the resolution in a 3D structure. Then the amplitude correction. Okay, so you have you have micrographs. These micrographs, as we saw yesterday, have been affected by a contrast transfer function that modulates the Fourier coefficients in different ways. So for instance here we are forgetting for the moment about the envelope, and we see that all these frequencies in one of the micrographs, the red one, have been multiplied by a number, and in the green one has been multiplied by a different number. So the phase correction is simply inverting the sign of these coefficients, but it is not compensating for the number that they have multiplied by. Okay? So these coefficients here have been multiplied by a very low number, and in your 3D reconstruction will be damper, and so you have to boost them up to recover the original size of those coefficients. And for this boosting up, what is normally done is to calculate CTF groups. So for instance, these two CTFs may be put into different groups, so that you put all the micrographs that have a CTF, or the focus, that is close to this red one. So you compute this curve for all the micrographs, you decide which ones are the most similar to the red, you put all of those in one single data set, and you make a 3D reconstruction. And then in this 3D reconstruction, you will be missing some points. For instance, this frequency here, this frequency there, they are missing. And you do the same for the rest of the micrographs. So the green one would go into a different group, and you construct different groups. For instance, in the XMIP, you can decide how strict you want to be with your groups. And there are people who make one group per micrograph, people that are gathering several micrographs into a group, or you may be as you like. So once you have your volumes for each one of the groups, you have to combine all the volumes. And this is done with a Wiener filtering that Javi was yesterday explaining. So at the end, what you will have is a single reconstruction that combines all the information that you have from all the data set through this Wiener filter. Another possibility to perform the amplitude correction is to go to more theoretical background. So it is known by this Wilson statistics that if you plot the logarithm of the intensities of the Fourier coefficients as a function of the resolution squared, so this is angstrom to the -2 instead of angstrom to the -1 as normally the frequency, it is known that for Wilson statistics, that are the statistics related to atomic structures, the Fourier coefficients should have a constant value. So I have my volume, I compute this plot, I get this thing here, and then what I do is to multiply by the difference between the observed curve and the expected curve. Okay? So I compute what is this difference, I multiply by that, and by doing this, I'm boosting high frequencies, and I go from this volume to this one. And this is called the Guinier plot. This representation is called the Guinier plot. And the factor by which you have to multiply is called the B factor. Right? It is a curve, in fact. It is a factor defined in a curve. Then there is a problem in the whole field of overfitting. So the overfitting in general statistical terms is something like this. So let's say you have a lot of measurements. Measurements for us are images, experimental images. You have to fit a model to those images. So a model for us is a volume, so you have to fit a volume to your experimental images. In this representation, a model is a line or a curve like this, and you want to decide what is the best model, what is the best volume that fits my data. So this is it goes more or less with data. This goes better with the data. For instance, this going up here is better represented in this other model. And this Other model goes very well with my data, but probably it's not a good model for this experiment, because it is overfitting. It is trying to adapt too much to the particular variations that I have. So here what you are doing is overfitting the noise. So when you do an overfitting in 3D reconstruction, what it happens is that you have a lot of artifacts. You are trying to fit too much the noise that you have in your experimental images. So a consequence of this overfitting, normally it is an inflated resolution. You think you have more resolution than you actually have. So there are several strategies to try to avoid overfitting. The first one is to do manual peaking. So if you manual peak, you are biased by your eyes, but you are not biased by an initial structure. So let's say that I use an initial structure to peak my particles. So I generate projections from this initial structure, and then I use these projections to peak my particles. Probably what we have seen with the Einstein, so what I will get is back the Einstein. So I'm reproducing my original structure. This manual peaking, if you don't want to suffer a lot, then maybe you can combine manual peaking with some machine learning algorithm that learns what you are doing and then tries to reproduce the same kind of peaking that you are doing. The other strategy is this gold standard that is now in fashion. That is the Fourier shell correlation idea of separating the two data sets, but to the extreme. The two data sets never intermix during the process, so they are completely independently processed with the projection matching. Then another strategy is to try. The problem with overfitting is that I try to fit too much to the noise, so I have to remove every place where I might be overfitting noise and I know there is no structure. And this is a standard practice in EM. For instance, in Fourier space, it is typical that from one iteration to the next, you limit what is the maximum resolution that you want to use for alignment. So I don't use the full Fourier spectrum to align in the next iteration, but just a part of it. And the same you do in real space. Normally you can put a mask and say, outside this mask I know what I have is noise, so remove everything there. I don't want you to feed anything in there. And you can extend these ideas to any space that you like. The wavelet space, you can impose a sparsity there or whatever. Also, during the angular assignment process, you can try to go rather slowly. So don't try to be too greedy. Don't do a very fine angular assignment from the very beginning. So if you are going to do 10 iterations of projection matching, don't do it from the very beginning with half a degree of angular differences. Then you can try to also remove a strange particle. So during my alignment process, I may decide, okay, I don't trust this particle. So this particle, for instance, in the 2D particle screening that Jose Miguel has been showing, so I may decide this particle, I don't understand it, it doesn't go with the rest, I remove it from the analysis. Or, for instance, these 2D cluster cores that we have been discussing before, they also help to identify bad particles. And this problem of bad particles is particularly strong now that we have automation in all the acquisition steps, so that there are many particles that maybe they don't correspond to your structure. Then this idea of 2D cluster cores, you can put it into 3D cluster cores, and then look for a particle and the particles assigned to the same direction to see if they go together or not. There are particles that are changing the angular assignment all the time, so if there is a particle that is jumping all the time from one position to another that is quite far, you don't trust that particle either. Okay, so you have taken all your care, and still, at the end, you have to validate that what you have obtained is the correct structure. And the three most popular techniques are these ones. So first, you have to see what is your angular distribution. So this is a representation of the angular directions of each one of the experimental images. So each point here is an experimental image. So these are top views, these are side views, and then in this example they have this angular distribution. So if you see that you have an angular distribution that gives you a lot of missing Fourier space, then probably you don't trust so much your structure. Then you have this tilt pair validation, that is, I take some micrographs in a tilt pair mode, so one untilted, one tilted, and I do angular assignment for both particles. And since I know what is the tilt angle, I should see this tilt angle in the difference between the angular assignments for the two sets of images. And this is a paper by Richard Henderson 2-3 years ago. And then also validation is through the fitting. So I fit an atomic model to my 3D structure, and if I see that there are many areas where the model doesn't fit my volume, probably I may have a wrong volume. So you may try to change something in your analysis so that you get a model that better fits your expectations with respect to the atomic structure. For instance, this is particularly important if you claim to have a resolution between 5, 6, 7 angströms. There you should see secondary structure, so the secondary structure elements should be consistent with your EM reconstruction. Here we have a web page with a repository of all methods related to 3D EM, so 3D reconstruction. All the list of papers that I have been showing, they are collected in this repository. And this is all from my side. This is a little bit what we have been seeing. So the full process, when you want to go to 3D, so you need to choose your initial volume. This is a really critical issue. Then the angular assignment, well, it can be more or less robust, but this is not normally the bottleneck. The 3D reconstruction either. So normally most 3D reconstruction algorithms work. Maybe they give you a little bit advantage with respect to resolution or something, but it is particular for each one of the cases. Then 3D classification is again one of the bottlenecks. So if you have a heterogeneous population, it is hard to classify, to sort the particles into the different classes. Then measuring the resolution, it is a long debate, but okay, somehow we produce a number. There is a silly competition of getting the smallest numbers possible. I think that the useful thing is to get useful biological information from your structure. And then you may apply this amplitude correction to, if you want to go to high resolution, definitely you have to do an amplitude correction for the CTF effects on the data. And then overfitting is again one of the battle horses in this field. So trying to avoid overfitting, especially now that everyone is trying to get 2 angstrom resolution, you have to be very careful with overfitting. So that's all.